All right, welcome back. Now we're ready. We know the Mordell-Weil theorem. We know that if I have an elliptic curve over Q, the Mordell-Weil theorem tells me that the rational points on an elliptic curve is a finitely generated abelian group, and in particular, there is a finite group that is the torsion subgroup, and there is a finite number of generators that give me the rank of the elliptic curve. And now I want to actually compute all these things. We know how to do the torsion subgroup. We proved the Nagel-Lutz theorem. And in particular, if I can put my elliptic curve in short values transform, the Nagel-Lutz theorem is a great tool to compute the torsion subgroup. We had other tricks in our sleeves, which were those embeddings into groups of points over finite fields. That is also very useful. So the torsion subgroup, we have it down. Now the question is how to compute the rank of an elliptic curve. Okay, so we want to compute the rank and we want to find those generators somehow. So what we're going to do is, for the time being, last time we talked about canonical heights, and what we showed is that, or what we explained at the end of the last video, was that if you give me points that are linearly independent, if I have R points that are linearly independent, then it's a computation, it's a finite search to find a basis of the Mordell-Weil group, okay, a Z linear basis of the Mordell-Weil group. Because if I have enough of them, then I can just look at their heights and then do a search of bounded height for points, and I will find the generators. So what I need is just R, like in the rank, linearly independent points that I can figure out their heights to then later find all the bases. So what we're going to do is try to find representatives. We're going to find generators of the weak Mordell-Weil group. Okay. If I find generators of those, then with a search up to a certain height, I should be able to find a basis, actual generators of the Mordell-Weil group. So what we are going to do then is take the easier case possible, which is when m is equal to 2. This can be done for higher values of m. It gets more complicated. But with 2, what we're going to try to figure out is what are generators of E mod 2. And that is going to be what? The torsion modulo twice the torsion. That, if you know some abelian groups, when you do that quotient, everything vanishes in that quotient except the 2 torsion. So whatever 2 torsion we have over Q, that will survive. So you might have surviving copies of Z mod 2. There might be 0 copies if there is no 2 torsion defined over Q. There might be 1 copy if there is 1 2 torsion point over Q, or there might be 2 copies of Z mod 2 defined over Q, plus, and then the rank, the free elements, when you do Z mod 2, you're going to get R copies of Z mod 2 due to the rank of the elliptic curve. Okay, all right. So what we're going to try is find a way to compute this thing. So here is an example case. So we're going to start with a very basic case where we have the full 2 torsion defined over Q. Okay, we're going to do it a little more general. We're going to assume, let's start with an elliptic curve over a number field. I can always extend my number field to have the 2 torsion. So this would actually, this works for every elliptic curve. It works better if the 2 torsion is already defined over Q. Okay, so let M be bigger or equal to 2 and assume that the M torsion is defined over your number field. Okay. Then we're going to throw everything we've learned to this problem, which is all the pairings we've learned through the course, the Coomer pairing, the Vape pairing, everything is going to come into play now to try to figure out this problem. So remember that we have the Coomer pairing. The Coomer pairing went from points on E cross the absolute Galois group of K to M torsion, okay? And it sends kappa of P and sigma to Q sigma minus Q, where Q is such that M times Q, sorry, is P, right? Remember that the kernel on the left is precisely MEK. We also figure out the kernel on the right, but the kernel on the left is M times EK, and therefore we get a map delta E from EK modulo MEK that goes into the HOMS of the Galois group into EM, such that delta E of P, the HOM that you get, is that when you apply to this to sigma, you get kappa of P sigma. Okay, here's where this already should, actually, if you watched the videos that I've made on cohomology, then you'll notice that this is the map. We explained that the Coomer pairing comes exactly from a connecting homomorphism between cohomology groups, between the 0th cohomology group and the 1st cohomology group. In particular, you see already cohomology showing up here because HOMS from the Galois group to EM, in this case, because EM is defined over K, because the M torsion is defined over K, the Galois group acts trivially on EM, and therefore this is an H1. And this group here is an H1. This is the 1st cohomology group of the 1st Galois cohomology group on EM, because the action on M torsion is trivial. Okay, great. Now, so we have a map, okay, that goes from EK modulo M into HOMS. And by the way, the Coomer pairing was, it was a perfect pairing, so this is an injection. All right, so this we used in actually to prove the weak Mordell-Weil theorem. We use this injection to try to figure out what was the a bound on the rank on EK modulo M. So we're going to use that again here. Great. So let me repeat that I have delta E that goes from EK modulo MEK goes into HOMS of the Galois group into EM, such that delta E of a point acting on sigma is kappa of P sigma. Great. Now let's recall the other pairing that came up in the course, which is the Vape pairing. So recall that we have the definition of the Vape pairing. In the definition of the Vape pairing, we started from a point of M torsion, and we picked F, a function such that the divisor of f was m times t minus m times o. Okay, that divisor is a divisor of degree 0, and when you add those points together, they give you 0. With m times t minus m times o, it's 0. Therefore, it corresponds to a function, to a divisor of a function. And we also defined a g such that the divisor of g was the sum of t prime plus r minus r for r of m torsion, where m times t prime equals t. Okay, and these two functions, the f composed with multiplication by m and g to the m, we saw that they were the same function up to a constant, so we can pick them so that this happens. All right, and then the pairing was the value of this for any x on E. It didn't depend on what point x you took. That was the pairing. And recall that the Vape pairing was bilinear. Is from EM cross EM to mu m, that it is bilinear, it is alternating, that it is non-degenerate, it is Galois invariant, and it is compatible. Remember what that meant. In particular, when yeah, so what we're going to do, why are we bringing this up? The reason why I'm bringing this up is that I'm going to consider the following. I'm going to take EM, and I'm going to evaluate it. Delta gives me a for every point, it gives me a homomorphism into EM. So I can write delta E of P evaluated at sigma. That will be an M torsion point. And I can pair it with a point, an M torsion point T. And now if I leave that sigma as a variable, so this is actually what's going to vary here. So this is the variable is right there. Then what happens? Then this is something that is a hom from the Galois group into mu m. Okay, but it turns out that every such hom is coming from a very specific form, and that is because of Hilbert's Theorem 90. So it turns out that Hilbert's Theorem 90, and this again, if you haven't watched the videos that I made about homology, but Hilbert's Theorem 90 tells you one thing. It tells you that H1 of the Galois group, of the absolute Galois group of K bar of the unit group, that this is 0. And in particular, it tells you, and we proved this in the video, that H1 of the Galois group on acting on mth roots of unity, that this is isomorphic to k cross modulo k cross to the mth power. But in here, if we assume that the M torsion is defined over K, then it is also true. Remember that for that to happen, from the definition of the Vape pairing, from the Galois invariance of the Vape pairing, we saw that this means that the mth roots of unity are defined over K. And when that happens, then the action of Galois on the mth roots of unity will be trivial, and this H1 is actually Homs. So in this case, this is the easiest case of Hilbert's theorem 90, basically, or the consequences. This is isomorphic to K cross modulo K cross M, but that is just saying that the Homs are always of a very, very particular form. And this means that every Hom from the absolute Galois group to mu-m is of the form sigma goes to an element beta, sigma acting on element beta over beta, where sigma, or where beta is an element of K cross, such that beta to the mth is in K. Okay, so what that says then is that so there is an isomorphism. In other words, there is an isomorphism delta K that is essentially from Coomer theory, but in any case, that K cross modulo K cross to the mth power is isomorphic to the Homs of the Galois group into mu-m. That sends for every B here, for a class of modulo mth powers, this is sent to delta K of B is the homomorphism that sends sigma to sigma acting on beta over beta, where beta to the mth power is B. Okay, so now going back to our pairing here, going back to this, so you see that using the Coomer pairing and the Vape pairing together, we got a Hom, so it's got to be one of these. So so it follows that E M delta E P acting on sigma T has to be an image of this delta K isomorphism. So it has to be delta K of some B, okay? And I'm gonna call that BPT acting on sigma for some BPT in K cross modulo K cross to the mth powers, okay? Okay, so this is going to give us, in the next lecture, I'll continue from here, this is going to give us a bilinear pairing, a new bilinear pairing that is going to allow us to compute the quotient of the Mordell-Weil group, the weak Mordell-Weil group, in a very computational way, or computationally amenable way. Okay, so in any case, we'll stop here and we'll continue next time to make this very explicit. In the case of m equals to 2, an elliptic curve over a cube with a full 2 torsion, to compute the Mordell-Weil group in that case, and then try to generalize this in a way that we can apply to a wider class of elliptic curves. Right, so I'll stop here and continue next time.